Now that we've established the scientific method, we are going to be generating lots of data from our experiments. And that's good that we are obtaining more information, but we don't want to just have information, we want to utilize it. So our tool for making this information that we collect actually useful is called classification. So this is the process by which objects are differentiated and understood. Now, the usefulness of classification is it allows us to make statements of the nature things classified as X tend to do Y. The reason this is so useful, say we encountered an animal that we had never encountered before. If we were able to classify it as a bird, that would immediately tell us about its bone structure and its organ structure and its weight to lift ratio. Now, we would probably have to still confirm those things if we wanted to be particularly confident in them, because there could always be exceptions. But classification is doing a lot of legwork for us without us having to be in the lab. So that's why we love classification. It's the tool in science that takes our scientific information and puts it in our hands. Now that we have our tool of classification, we're going to want to take it and use it in what we said we were interested in, which was the study of matter. So there are many different ways that we can classify matter. One very important way, which is what I'm going to introduce here, is we can classify it by phase. A phase sort of encompasses a broad number of properties of the substance, especially at the small microscopic level, which we'll learn about more later. So there are many different types of phases, but we are going to restrict ourselves to just a few of them: gas phase, liquid phase, and solid phase. These phases tend to describe most substances found under standard conditions at the Earth's surface. So a solid is pretty straightforward. Here we just have something that's of rigid shape. Liquid is a little bit more versatile. It's a fluid, and what it will do is it will take the shape of its container. Finally, we have a gas. It is also a fluid, and like a liquid, it will take the shape of its container, but even better, it will expand to fill the volume of the container. So the liquid, can only take the shape of probably the bottom of the container if gravity is present, but a gas will automatically take the form of the entire container. Another form of matter that we can have is what's called a colloid. And what a colloid is, it's actually two of these other phases interspersed with one another. And that's interesting because it can lead to new properties which are different from the properties of any of these other two substances independently. As an example, we might consider fog. Fog is a colloid. It consists of little water droplets, so that's a liquid, suspended in the air, which is a gas. Now, if I were to shine a laser through a cup of water, it would shine straight through. Water is transparent. Same thing for air. Air is transparent. If I shine a laser through it, it will shine straight through. But what if I do that for fog? Well, fog tends to be opaque in the visible spectrum. That's why we have to have things like lighthouses in order to help boats navigate in it, since it's hard to see through. And the reason it's opaque, if we imagine a light coming in like this here, if this was a cup of water, which both of these would change direction a little bit in the same direction. However, with fog, this light will scatter some random direction because of this droplet, then it will scatter some other random direction because of this droplet, and we'll wind up going some random direction on the other side. Same thing here. This encounters different droplets, so it gets scattered in different directions. And so now my light is no longer coherent. It's no longer shining the way it was on the other side. So it's no longer going to accurately represent whatever object it reflected off of. So now we have a new property because it's a colloid. If we can glean some information about what our substance is made out of, then we can classify it by composition. So we'll introduce a term here. The term is mixture. It's just two or more substances mixed together. So that's the same way we use it commonly, same in chemistry. And to classify matter, then we can classify it as a heterogeneous mixture. That's where we have two phases mixed together. Like fog, we had liquid mixed with gas. We could also have maybe cereal or ice water would be solid mixed with liquid. What's important is that we have at least two of those. Conversely, we could have something that was homogeneous, and if it's homogeneous, that means it's the same phase throughout. And we could have something pure like water, or we could have something like salt water, but in both cases, it's a liquid for its entire consistency. How are we going to distinguish whether we have the heterogeneous mixture or we have something that's homogeneous? Ideally, we'll be able to just look at it and tell. If it's something like cereal, we'll definitely pick out there's solid bits mixed in with liquid bits. Something like fog, though, that's more difficult, right? You don't really see those water particles in fog. So what you have to do here is you have to go ahead and just zoom in. Let's say zoom in 10,000 times. And so we do that for water. We zoom in 10,000 times. And then it's going to look the same. We zoom in 10,000 times again. Still going to look essentially the same. Fog will be different. You zoom in 10,000 times, and now it looks like you can kind of see those little water droplets. Zoom in 10,000 times a second time, and they become very pronounced. Now, the 10,000 has some significance here. You don't want to keep zooming in more than this. If you keep zooming in, you're going to start seeing things like molecules and atoms and subatomic particles, which we haven't discovered in our course yet. And if in that case, you would say everything is heterogeneous because everything is made of these discrete subunits. Compared to a colloid really has particles on the size of between 1 and 1,000 billionths of a meter. So if we zoom in 100 million times like we're doing here, that will put us in that range where we're likely to see them. And so in the heterogeneous case, we should see visual dissimilarity between the different regions, our water region and our air region, something to demarcate the different phases. For our homogeneous, zoom in, all the parts of the picture will look the same. Heterogeneous substances, we know can be separated. If I have cereal, I can definitely pull out the cereal granules and then have the solid and the liquid phases as distinct again. Can you do the same thing with homogeneous substances, though? Can you separate them into other independent substances? Well, if we were to go out and make a determined effort, what we would discover is sometimes they can be separated and sometimes they can't. So that means we have a dichotomy. We have two separate cases. We can make a classification between them. In the instance where we can't separate them any further, we have a pure substance. In the case where we can, we have what's called a solution. Or another word for solution is homogeneous mixture, which you can compare to our heterogeneous mixture here. So solution, we have substances of the same phase mixed together. Heterogeneous mixture, we have substances of different phases mixed together. Or we could just have a single substance. So an example of a solution would be something like salt water has salt mixed in with water, and it's all liquid. And if we were to leave out our container of salt water, eventually the water would evaporate and leave the salt behind. So then that's yes. We can definitely separate out the salt from the water. However, if we just had the water sitting in front of us, the water might evaporate, but we would never look in the bottom of our container and find a different substance left behind. The water just stays as water the whole time. That makes it a pure substance. How do we tell if we have something that is a solution or that is a pure substance? We could certainly try separating it into components, and if we can do that successfully, we have a solution. If we can't, we may eventually start to suspect it's actually a pure substance. But what if you're just thinking about it and trying to decide whether you should list something as a solution or as a pure substance? My hint to you would be that if it's a solution, since it's made of multiple components and you could have varying amounts of those components, that means that it's going to vary in its properties. So you could have slightly salty water that had a little bit of salt in it, or you could have very salty water that had a lot of salt in it. Conversely, if you had a pure substance like water, separating the components of a heterogeneous solution is not too difficult. We can maybe use a sieve or some fine mesh paper or something to filter one substance from another. But that's not going to work for a solution because both substances are in the same phase. So they'll both pass through the sieve, they'll both pass through the filter paper. So how are we going to separate those? Well, there are a few methods which are common. One of these methods is distillation. This is where we use a difference in boiling point to separate substances. We mentioned doing this for our salt water. We could evaporate the water from the salt. We could increase the evaporation rate by increasing the temperature. One of the first uses of distillation was to distill alcohol. Aristotle wrote about this in Meteorologica, so it's been around since at least 200 BC in ancient Greece. And so the basic idea here, we're going to have our mixture of water and alcohol, which might have come from our fermented grapes. So we have some wine in here. And alcohol has a lower boiling point than water, so it's going to tend to evaporate first. And a larger fraction of this vapor is going to be comprised of alcohol. Now, there's still going to be some water evaporating. Water evaporates even if we don't heat it, so it's still going to be part of this vapor cloud right here. But a higher fraction will be alcohol. So now we cool it, and in the lab you usually use a water jacket where you have running cool water to cool down the vapor. And so it will condense and it will drip into these containers here, which now have the higher alcohol content. And if we wanted to increase the alcohol content further, what we'd have to do is we'd have to dump these into our main vessel here, and we'd have to repeat the process. And we might have to do it quite many times in order to get a very concentrated solution. Another way we can separate substances in a solution is by capitalizing on the fact that they're going to interact with other substances differently, depending on what they are and what those other substances are. And this is called chromatography. It's a very powerful technique. It's led to Nobel Prizes, such as for the discovery of the components that make up our DNA. And to understand how chromatography works, let me draw you a picture. So imagine we have a room, and there's this crowd standing outside of the room, and they're all anxious to be moving on their way, so they're all pushing and shoving each other through this room. And in this room, there are some reporters, and reporters aren't interested in leaving. They are just interested in talking to people in the crowd and getting the scoop and finding new stories. Now, mixed in with the crowd, we also have some introverts and some politicians. Now, the introverts, they don't really like to talk to people. And so when they go through this chamber, what they're going to do is they are going to try and move around everyone. And so they'll get through very quickly. Conversely, we have these politicians, and the politicians, first of all, they're interested in talking to other people in the crowd. They want to find eligible voters and convince them to vote for the politician in their re-election bid. Additionally, we have these reporters, which the politicians definitely want to talk to and sort of tell them, what their campaign is about and what they're doing and generate some interest. And so these politicians interact more with the crowd. They interact more with these reporters. And so they are going to take a long time to navigate and to escape. So the crowd represents our mobile phase, the reporters represent our stationary phase, and then the introverts and the politicians are the two substances that we're trying to separate. So what happens is the introverts, they all escape the room first, and then we could, close the doors or cart them away in a train or something, and then the politicians will come out later, and then we can cart them away, and now we've separated the introverts and the politicians. This is exactly how chromatography works. We just have substances instead of people. We have molecules go through, and we have some embedded molecules in there to make our stationary phase, and one of our substances is going to interact more strongly, one more weakly. Same thing for our solvent, which is what we're using to push everyone through. And so then all we have to do is just wait for the first solution to come out and then the second solution to come out, and we'll have successfully separated them. Let's push forward with our line of questioning. So we realized that heterogeneous mixtures could be separated, and we asked the question, well, can solutions also be separated? And we found out that yes, they could sometimes. They could be separated into pure substances. Well, if we have those pure substances, something like water, is there a way that can be separated into other substances? The answer to this question is, again, sometimes, depending on which substance we are considering. And so that means that we have another bifurcation in our classification scheme. So we have our pure substances, and if we are able to separate those into other pure substances, then that is a compound. If, however, we are unable to separate our substance, then we have an element. Now, how would we separate pure substances? We'd have to actually do some chemistry on it. We can no longer just run our substances through a physical device. We have to perform chemical reactions in order to separate them. And so that's what's happening here, is some chemistry. And if no chemistry can further separate our substance into other substances, then we have elements, which are indivisible as far as chemistry is aware. And so they provide the basis of this chart. They can be combined into compounds, and as pure substances, these can be combined into solutions. And these homogeneous things can be combined together to form heterogeneous mixtures. And so this is our full classification scheme of matter based on its composition. An example of a compound you might be familiar with is something like water. You may have heard it described as H2O. This is a notation which we will describe more fully later, but it indicates that water is made up of hydrogen and oxygen, and so we can separate it into hydrogen and oxygen. But we can't separate the hydrogen any further, and we can't separate the oxygen any further. And that's because hydrogen and oxygen are elements, which combine together in this compound to make H2O. Which could then. The final classification that we're going to introduce at this point is the classification of changes. So the first type of change that we will consider is when we have a chemical change. So this is where new compounds are formed, and the way they're formed is going to be by a chemical reaction. And An example of this would be, for instance, if you were going to burn a match, you would no longer have the phosphorus and the paper that made up the match. You would have new compounds. And a clue that you have a chemical change is that these are usually pretty difficult to undo. You're not easily going to be able to go and find all the parts of the new substances and recompose them to get your match looking like it was brand new. Now, because we have this kind of change, that means we have at least one other kind of change in our classification. And our other kind of change is physical change. And this is where our process does not affect the chemical composition of the substance. The compounds will remain the same. An example of this might be distillation or chromatography. And your clue that you have a physical change is that there's some way to easily undo it. Now, distillation, say we've distilled some wine into alcohol and water. How can we undo that? We just have to mix them back together. So pretty straightforward, good clue that it's a physical change.